Analytics, that's doing queries involving lots of rows, right? Transaction processing, OLTP, your operational data store. That's the thing that's actually on the front lines responding to requests. So how many people know what TLDR means? Okay, we got about a third there. My co-founder didn't, so I passed the slide deck one. He's like, what the heck does that mean? So that means too long, don't read. So if you don't remember anything else from this conversation, I'll present this again at the end. So what we found is that most databases doing analytics don't operate on a row-by-row basis. They operate on tables. They're using streaming disk subsystems because that's what we have, right? We had, until now, disk was really the only storage system that was available. So what we found at Aerospike is row-based is easy to scale, and I'll tell you why, but basically it's big hash table scale. And that's really, really fast for the kind of operational transactions without joins, denormalized operational transactions. Big hash table, right? Turns out it's really predictable for analytics because you don't have the problem where you have rows all next to each other and noisy neighbors. So it's super predictable. And it turns out it's fast because you can use lock-free, fine-grained locks and different scheduling algorithms. And when you use that with Flash and RAM, you can get a lot of the power of the other systems and still hit higher levels of scale. So this is very much in-memory techniques, but I'll also tell you what role Flash is playing in making all this stuff a reality. Okay, so back off for a second. What's the database landscape? We've got all of our old friends in OLAP and OLTP. Now we've got our new big data friends. We've got a nice friendly elephant out there. And we've also got now architectures that have an operational store, usually for behaviors, right? So in terms of financial services, that might be your fraud database. It might be transactions, user profile state. And in advertising, which of course this is the hotbed of the universe, is probably here plus about 7 blocks, for user profile storage within advertising. That's the stuff that's on the front line, allowing you to optimize moment by moment for different ads. So the challenges of trying to build a database for this kind of system, for very high scale profile storage, very high levels of reads and writes. So unlike a lot of systems and a lot of content management systems that are heavily read biased, and a lot of analytics systems that are also heavily, they tend to be all write for a while and then all read for a while. They don't tend to mix their transactions, right? But the operational data stores that we've had to build at Aerospike reads and writes at the same time because you need fast changes based on behavior. Hotspots. You got to avoid hotspots. That's the way you make sure that your database stays operationally predictable. You want to provide consistency. You want to provide linear scale. And especially being able to add capacity without service interruption. And that's really what these new internet enterprises need. Google doesn't go down, at least not that much, right? My Gmail gets a little wonky now and then, but it's pretty much okay. And it's all very fresh, it's all very behavioral, it's all very personalized and customized. So in order to convince you that I actually know something about this topic, this is a small portion of our customer list. It's about half of our deployed customers. So if there's names you recognize up there, some of them like AdChina, largest advertising company in China, Exalate right around the corner, great company selling data, buying and selling data. AppLovin, I think the strangest name on the list, that's Nick Lovin, basically is what they named the company after, but it's for mobile apps. So a lot of folks out there using our database, and also Mike had a great quote that came out in Information Week regarding our database. So I suggest you check that out. And we are founded by a bunch of, my co-founder, Srinivasan, is an old database hand, University of Wisconsin. I'm more on the networking and distributed systems side, and we're funded by a combination of Draper Associates, if you know Tim Draper. It seems like he's on television doing some of the VC stuff a lot. Alsop Louis, which is a boutique firm out of San Francisco, and NEA, one of the largest firms in the world. So what's necessary about these operational stores? Predictable latency is one of the hallmarks of being an operational store. You have to be able to present not just good throughput, but you also want to see your throughput be very stable in latency out towards the edge of your curve. What you also want is a system that will stay stable even in the face of downtime and hardware failures and switch failures. So some of you guys are operational and you've actually had the problem of switches going down, rack failures, PSUs blowing, all that kind of stuff. If you need your system to stay up, as is necessary in a lot of these internet systems, exactly the characteristics of failure in these clustered databases is absolutely critical. There's a company, I think they're actually based out of Dumbo, and called Thumbtack Technology. They're a partner of all of these different companies, us, DataStax, Mongo, and also Couch. They wanted to do a report to try to help their customers sort through who's who in NoSQL, because they deploy a bunch of all of this kind of stuff as consultants. And so they did a benchmark. So all of these numbers are based on the Yahoo Cloud Serving benchmarks, YCSB. It's all downloadable open source code, as well as their report on the different scale factors, as well as how the different databases respond when you're actually seeing a failure. The way that we're able to do this as an operational store is through a shared nothing clustered system. And the benefit of this system is the distribution system being row by row. So just standard distributed hash table is one of the keys of scaling in a lot of these systems. But we've taken a few different twists to it. You can think of this as your homegrown sharded system where we have a large number of shards, but we can move them around moment by moment based on operational failures, loads, replication counts, increases in capacity. The benefit of what we're doing here, different from some of the other systems, is the form of random distribution we have of the partitions. So if a particular partition is mastered on node 2, its replica is then randomly chosen as well. The benefit is when one of those machines stops working, a random number, a particular number of shards become slow and then have to be re-replicated. But that load is the same across the entire system. So the predictability compared to, say, a corded system, right? So in a corded system like Mongo, it's the next server in the chain that has to be replicated becomes hot. So what we've really done is to become a really great operational row store, really great key value store, we had to really think through how to make the system super random so that you never ever get a hotspot. And when you do have to recover from an operational problem, it happens pretty manually, automatically. It happens very automatically, and it happens with the least operational impact. Because as you get larger and larger clusters, you start seeing more and more failures. Now this system is built to have a modest cluster size. So it's not built for cluster sizes greater than about 100 servers. What we find in those servers is Cassandra-style architectures are actually superior because they, since they don't have as much node-to-node communication and synchronization, they don't need to synchronize, and they can be more robust in the face of larger and larger failure sets. Now, we have some architectures for larger clusters, what we call superclusters, clusters of clusters. However, we've also found that we don't actually need to do them for most problem sets. Some of our larger customers like AppNexus are commonly running north of 1 million transactions per second. That's the real-time bidding load right now within North America. We have one cluster that's spec'd at 5 million transactions per second, and we're at about 10 servers with modern servers on this system. So one thing I like to say is if you've got 100 servers in your cluster, maybe you're doing it wrong. The other possibility is that you actually have a multi-petabytes problem, in which case you should be on Hadoop. This system is good up to about 100 terabytes. With some of the new flash subsystems, it'll be good up through about a petabyte. But you can do that all with modest-sized clusters, which is beneficial operationally because you don't have as many failures per cluster per unit time. So we've focused on that particular area. I'm going to skip. Let's go through in this order. So an important thing about being a row-oriented architecture is to touch as few servers as possible, especially on an individual write, and still maintain data consistency. You'll see how this impacts analytics and analytics workloads in a minute. So the way that we write data is there's a master and a replica, but that's only for transactions and for data, like I said, with the partition system. Operationally, there aren't master nodes or slave nodes. All nodes are the same. Every server has essentially, if you think in Hadoop terms, the name node map is baked into it. So you don't have any extra shard system or cluster servers that you have to keep up and running. If the cluster's up and running, then the naming system and sharding system is already up and running. So what's interesting about the system in this is that row by row is where you have the individual locks and the individual atomicity guarantees from a database sense. So row by row, we take a latch as we are getting the data replicated onto the other server. The benefit is, since it is a row by row atomicity guarantee, you can get a higher level of scale. And that's very important to operational systems where predictability is key. The client also knows about this same row map and the same transactional guarantees. So the client library isn't simply HTTP talking to some particular server. It actually has to be aware of where the data map is so that it can talk to the server that is master or one of the replicas for this piece of data. That short circuits one network hop, which is absolutely important in this day and age. So we offer clients that have for C, async C through libevent, Java native, C# native, and then we build a lot of the other languages like Python, Ruby, Erlang, etc. on top of that. And of course, Scala is built on top of the JVM-based system. So let's get over to Flash, because that's things get a lot more interesting here. So the benefit of doing row by row operations for analytics is already kind of well known for in-memory databases. The problem with in-memory databases like HANA is really only the cost, right? So, and I'll take you through that. Actually, let's do that right now. The next slide. So, I just went through Dell's price list recently, trying to show sort of what the difference is between two different configurations. Now, Aerospike supports both RAM for some data sets and also SSD for others. Most of our customers run a blend, but these numbers are pretty impressive. And this is even fairly expensive flash. So in order to get the TPS per server at that high a load, that's at the same point where the network becomes the bottleneck. For a standard 8-core or 12-core machine, it's very hard to push more than about 500,000 TCP transactions in and out of a server already. So that becomes the bottleneck. If you can get your flash also running at 500, what's the point in actually going to RAM at that point? So for row-based operations where you're simply, one transaction, operational store, get that row, get out of Dodge, suddenly Flash becomes really the broad middle of storage solutions, direct attached flash. This particular device that I priced against is called the Micron P320H, which I mentioned the last time I was here in New York. So I'm not going to go too deep into the new current flash devices, the prices and the trends in that area, except to say that I'm really excited. Flash Memory Summit. So a lot of the social network companies have really figured out the value that Flash brings to their application, because they can create richer applications with a lot more capabilities in terms of finding all of your friends. That soaks up a lot of transactions, your friends of your friends. All of that social graph work is very well suited to a random row-based system, and Flash really helps. So we know that Facebook and Apple contributed $200 million to Fusion.io's bottom line. At the time, Fusion.io was one of the few suppliers of Flash to the enterprise. We know this from Fusion.io's public filings. At the Flash Memory Summit in Santa Clara, which was about a little over a month ago, Facebook had a really interesting keynote where they talked about this architecture. They talked about how random access in the database was really driving what their application could do, to the point that they've doubled down and they're buying an exabyte of flash hardware this year. Now, according to my calculations, that's maybe about $1.2 billion worth of flash hardware. They might be getting a deal. Some people are saying that Apple paid maybe 50 cents for their flash, and there certainly is flash priced that way, and at these volumes they might be getting it. So the 1.2 billion, that might be lower, but it's somewhere around $1 billion worth for that exabyte of flash that Facebook is buying. Now what they're doing is they're doing that direct attach. They've got their own database hardware, and they've got engineers that have optimized versions of MySQL and also some of the other database systems to work with this. But they know the power of this kind of random system where you don't have to rely on the streaming optimizations that were necessary back in the old rotational disk days. So back to this particular picture, what we basically got is the fact that RAM, I just picked 200 gigabytes for this particular picture because that was the sweet spot right now in Dell's price list of price per byte. So if you want the lowest price per byte, you actually have to buy nearly 110 servers to get all the way up to a 10 gig system. Now, people who are implementing HANA will tell you they will typically buy a terabyte per server, but they'll pay a premium to get that higher density and those particular kinds of servers. So you can build something like this with only 20 servers, but you'll actually do it at a higher price than this particular bottom line. When I present this normally to a flash conference, I point out that, if I'm trying to talk my VP into a new project, I might be able to talk him into $200,000. I'm going to have a heck of a time with new math, new optimizations, talking anyone into $4 million. That's kind of hard in this day and age. So if you want to start out, you definitely want to be in Flash. And if you can get similar performance, why wouldn't you be there? I was giving a version of this in China, and the guys were like, wait, we don't even have 10 terabytes. And we care very much about price. And I did a whiteboard pencil for them, and I showed them how they were going to save $20,000 just on the first 200 gigabytes, flash versus RAM, and both were going to meet their speed requirements. So, do you want to, who doesn't want to save $20,000 right off the bat using a flash optimized system? And that was based compared to Redis. So these numbers are pretty exciting, and they're only going to get better. What I saw in the Flash Memory Summit out of Samsung's 3D Flash, Intel's new roadmap on 2D Flash is everything's going to get denser and denser and cheaper per byte over the next 5 years for sure. These roadmaps are showing things like 10 terabyte, 2.5-inch drives, 10 terabyte laptop-sized drives. Okay, that's what's on there. Everyone's roadmap for about 2-ish years. This is all public. Samsung basically blew the world away when they presented their, at Flash Memory Summit, when they presented their keynote showing their entire 10-year roadmap, showing that they are on Moore's Law curve for Flash of denser, and they're going 3D. Everyone thought that maybe lithography was going to start having a problem because of cell size. Once they went 3D, started stacking bits up. It's a whole other world again, and we've got 10 years worth of 18-month doubles. Now, it's not going to go any faster, is the unfortunate thing. Just like CPUs, we've hit a clock speed limit. So don't expect Flash, it might get a little faster, 20% here and there. The speed you're seeing now, the optimization patterns that are necessary now, that's what's going to happen for the future. However, we're going to have a higher density, lower cost per byte. My crystal ball says that rotational disk and Flash will probably cross paths in about 3 years. At that point, there's not going to be any point in buying rotational disk for anyone. So,
when you say cross paths, what do you mean?
The price per byte.
Okay.
So right now, price per IOP. So if you're speed sensitive, Flash is already a winner 10 to 1. If you're price per byte sensitive, rotational disk still has, maybe a 5 to 1 edge depending on where you're getting your Flash and what speed you need. 5 to 1, maybe even 10 to 1. That's going to erode very, very quickly, especially with Samsung's new offerings. We don't know exactly how they're going to price them, but Flash is I think, predicted to go under rotational disk price per byte in about 3 years. And at that point, you're just going to say, well, that's the end of rotational drives. Just like paper tape. Anyone still using paper tape? Anyone remember paper tape? Excellent. Okay, so the point here is that all of the optimizations that you've heard about for in-memory computing are also available with Flash, Scale, and Dynamics. So One of the reasons I had the trivia questions about Michael Stonebreaker was he was one of the ones who popularized H-store and C-store, column stores and row stores. And with his Vertica engine, really showed the power of using column stores for analytics. What I'm going to point out here is there are some problems and some problems that are better solved with analytics on a row-by-row basis if you can make rows scale, just like I showed you in the previous section. So how would you do that? Well, you still need to pick a particular subset of those rows for processing. Because if you have a table scan problem, you should probably be using Hadoop and be getting advantage of all of those table scans. However, the processing involved in any analytics system is very much based on the individual rows that you have and picking up a particular row. Once you have it in L1 cache on your CPU, it's very fast to deserialize it, do whatever kind of operations, do any kind of rich operations you want. Those happen very quick. It's really the data motion of getting the storage, the bytes from someplace on storage over onto your main CPU core and getting a thread to actually be acting on it and then do that work. So a lot of the overhead really is row-based. So if you want to have a query system based on rows, the first thing you need secondary indexes that simply have references to the primary indexes. This means you don't have in database speak, you don't have multiple materialized views. You only have one materialized view, and then you have a lot of indexes pointing at it. So the benefit of that is when you have this primary key index in this storage layer that is also very random, you're still going to get the smoothness of a system in your query system. So there's an optimization pattern, you're probably used to it if you've heard about graph databases, of trying to put your graph and localize it all on one machine or on different machines and trying to push the data around so that it's co-located. Well, that's a really good optimization for some data sets. However, it becomes a real problem because then, well, what if you add one link and suddenly you want to move half of that data somewhere else? You're constantly playing this game of moving back and forth based on your data pattern. And in my experience, that's really one of the real problems with predictability. Once you have your performance dependent on your data pattern, you're going to have a lot of these things, and you see this actually in MongoDB, right? Because they split their data at different points. You insert a little bit, then it has to split. Then you insert, then it has to split. Same thing with those kinds of graph databases. Whereas if you stick to row by row, and that row is going to be planted on a single server, and the indexes for it are on the same server, you've got a very high level of predictability that is independent of the individual system. Another point to notice here is indexes don't really have to be persisted in the modern age. And this is one thing that we've found out at Aerospike is if you have multiple HA servers, well, that index is already on another server. The data is safe. So we use one technique, which is with our indexes, which are in memory, we can restart the process and not lose that memory. You put it in shared memory storage, you push it off to the side, and then you can restart your process, reattach to it, and Bob's your uncle. Just within seconds, you can do a process restart. Now, if you have to do a full restart, at least you've got the power of Flash underneath you, actually helping your rebuild times. So we commonly find in a full cluster restart, maybe a rebuild time of about 15 minutes. Now, that only happens when you're really shutting down a data center. And frankly, getting your data center back up in 15 minutes is usually considered to be a pretty good thing already. So we haven't had a lot of complaints about that. So if your secondary indexes are working in memory in this kind of scheme, what that means is your query has to go touch all servers, right? Because you don't know where it is, so you've got to go ask everyone. So this kind of optimization is powerful when you're touching multiple rows. Now that's primarily an analytics style solution. MapReduce is another way of looking at these kinds of queries, but it's an indexed form of MapReduce. So instead of thinking about MapReduce as a big table scan, you can still think of it as a query over a collection or a subset of your data. That's one of the most powerful ways to get a speed improvement in a MapReduce style of programming because you're touching many fewer rows. as I said, what we found is that the number of rows you touch is really the barrier to speed in a lot of these systems. It's not so much the IOs anymore, and it's not so much the network anymore. There's still some IO penalty in there. You can answer some of that by going with pure in-memory if you need to. But being able to simply touch 1 million rows instead of 1 billion, that's a huge win. So if you can do that one bit of indexing, if you can find one initial index to your MapReduce pipeline, think of it as not just MapReduce, but in fact a filter pipeline in terms of SQL, you can actually get very, very good performance. So in the ad tech world, this kind of thing would be, say, let's say I want to calculate the current value of a campaign or the last 10-minute touches on a campaign. I might have an index on time, so I touch only rows that have been changed in the last 10 minutes. That's not that many. And I can do a full recompute of statistics based on that very, very rapidly, in a matter of seconds, in fact, and still use the MapReduce tools that people know and love. Once you take that step of MapReduce, bringing this all the way out to a SQL-style optimizer with predicate analysis is not that far along. And I think everyone's been considering that the benefits of NoSQL scalability are going to be moving into using more of the SQL language predicate systems. There's already a lot of subsets of SQL. Mainly, I think all of us are trying to stay away from trying to implement an entire SQL, especially with large joins. Large joins are inherently fairly non-scalable and are best done on single servers. So our strategy is to try to not allow people to do the kinds of operations like that. If you're doing that, stay on a relational system, stay on a vertical scale system. There's a lot you can do without large scale joins. So the takeaway from this point is that the selectivity of a query, the number of rows you're touching, really is the best determinant of the amount of load on a database system. So what happens if you try to combine your operational store, that is your OLTP store that's on the front line of your service, with doing some analytics? Now, it's not going to be all of your analytics, right? You've still got those big warehouses and you've got your 20 petabyte Hadoop store back there. But what if you're trying to do some analytics on that side? Typically, that's considered to be, fantasy. You wouldn't try to actually do large queries on your operational system because it'll slow down, it'll get hurt, it won't be able to respond predictably. So imagine a system like this, where you have those operational single row key value store requests coming in, and then you've also got these queries coming in of the style that I mentioned that are all being filtered through this secondary index. All of them have to go to the primary key index in order to access a row. Now, all of your load is on a row-by-row basis, which means that this is the perfect choke point to do your prioritization. This allows you to do deadline scheduling of your operational queues. If you've got 10 milliseconds to make a database request and it's been 20, you kill it right there before it actually impacts the rest of the system. Part of the system has the most load, which is here. Similarly, you can stream these index hits into this subsystem and allow that to trickle through according to whatever prioritization scheme you'd like to have. So there's a lot of benefits to this system. One is the scheduler in a distributed system can get kind of tricky because you're often trying to look at the effects on different systems. The benefit of this falls out of the fact that it's a very random server-by-server system. So the fact that it's randomly done means you can calculate and do your priority queue scheduling on this one server and have it be correct for all of the other servers at the same time with no coordination, which is one of the deaths of distributed system. Rows are also very fine-grained. Now the point there is you can still do writes to this system and not be blocking a lot of your analytics queries. Now you're still going to have to worry about consistency there, right? Because it's a distributed system and you've got writes during your query. You're going to get one answer or the other. You're guaranteed not to get both. You're going to get one version of that row if you have a write coming in at the same time. There's sort of not a way around that. If you want parallelism and you want this kind of capability, you have to give up a little bit and allow the row to be the atomicity guarantee in the isolation domain. So based on that, what are some of the common thoughts you might have about building an operational store and a hot analytics store. Well, the first idea is, you know what? The biggest problem with running these things is actually sizing them correctly, so that under a particular level of load, did you buy enough hardware? Well, the good news about using this kind of row-based system for doing your computation is your calculation of server cost is you say, well, we can handle this amount of selectivity of your queries. Well, is it this kind of a select? Is it an order by? Is it X? Is it Y? All you need to do is figure out the number of rows those queries are going to touch, and that's the size of system you have. So the exact ins and outs of the queries are much simpler, allowing the DBA's life to become much easier, and then allowing you to size your cluster appropriately. Because as a software guy, if you don't have enough hardware, there's only so much I can do, right? There's a law of physics there at some point. So it becomes easy to estimate. Second of all, you can simply add a new cluster node. Everything I just said about the scalability of the system applies by simply adding a new server. You don't have any data locality, so adding a new server, randomly pushing some of that data across, allows you to simply get the right kind of scale. Second challenge with these kinds of systems is just what's the size of my cluster that's needed. You can be scalable, but then simply be unaffordable. Well, the system that we've already proven out, and the numbers we showed from the first portion of we're showing very high performance numbers of 500,000 rows per second against 500,000 rows per second against Flash. And internally, when not going across the network, we can easily hit 5 million to 10 million rows per second, even when invoking user-defined functions as you would do in a MapReduce. So 10 million rows per second on a fairly commodity, say a 12G Dell server, we think allows you to actually hit some pretty interesting performance numbers. Third point I think I sort of already made before, which is often in DBA land, you have to sit there and think about exactly the forms of the queries and the impact that query is going to have on your system. When you simply say, I don't care what the query is, I only care about the number of rows touched, you're able to calculate, and as your data shifts, you also don't have to create new indexes. Well, you have to create new indexes to touch fewer rows. But you can also simply say, well, what's the trade-off? If I'm not going to create an index, well, then I'm going to create going to have more rows touched. Then I know what the cost of that is. So the ability to predict the scalability of the system and whether to create a new index becomes a lot clearer. So the first three points were really about trying to avoid degradation and make your database fast enough for your load. The fourth point is a little more interesting theoretically, which says, okay, I still have peaks. I still have a query that I didn't really expect. It had a higher selectivity. What's actually going to happen to my core database? Well, the benefit of this kind of architecture is, going back to it, the fact that this priority queue allows you to very cleanly separate out the load and allows you to do scheduling according to some very normal priority queue style algorithms. So you can make sure, dead sure, that that operational load is getting through, even if it chokes out your analytics. Or it can allow you to allow your analytics to continue happening even to the detriment of your operational store if that's the policy you want. So this system offers very graceful degradation. And these forms of heap-style priority data queues are very, very well understood in RAM, and the capability of scaling them out to multi-cores actually works very well as well. I was thinking about this as I was writing the slide. An interesting point is when you have a partial result from one of these queries, since the underlying block store is highly random, your partial result is an unbiased sample. So what that means is, if you did a query and you only got 10% of the data back, in a standard database, you might just get the oldest 10%, right? But in this, you're actually going to get a random 10%, which allows you to then infer statistically what the rest of the system is, the query is going to be. That can be of great interest when your database is under load and you're only getting partial responses. Okay, fifth point about column stores, since I was going to get back to Mr. Stonebreaker and all of his efforts. There is still a point for column-oriented stores, because only touching data and touching a subset of the data, because you only really want to look at one column, is another way of doing this, and there will be cases where this outperforms a row-based store. Now the challenge is this one. So if I'm doing a column-based store system, I have to write different materialized views. I have to write different versions of the columns in different spots on disk, right? So depending on how I lay out that data, queries are going to perform differently. Okay, that's not so bad until someone says, hey, let's change the query pattern, let's change the schema. Then suddenly you have to rewrite your database, not just an index in memory, but you actually have to do agility and improving functional changes. However, this kind of optimization can still go faster than the kind of row-based system. It's just less flexible. So, last point. There's going to be still a fear of trying to run some analytics on your operational store. Until this kind of technology gets proven out, until you see it in production, I wouldn't trust it either. I mean, you hear some crazy guy in front of a room in a meetup, and what does he know, right? So that's okay, right? What we've done at Aerospike is we have cluster replication that is high availability and distributed. So if you want to create that analytics store and have that operational store, have that be separated for a period of time until you see how the whole thing plays out, possibly with different cluster sizes, fine, go ahead and do that. It's a very natural thing. Nobody has really said up until now that it's possible to really bring these two stores together in a predictable and safe fashion. So we're expecting that. It's fine with us, and we have an answer for that. It's our cross-data center replication product, which can also be used inside one data center in the case of wanting to have an analytics server cluster as well as a operational store. So a little bit about where Aerospike is on the journey to this particular world. We've recently released Aerospike 3. It went GA 8 days ago. And our goal was to create the modern real-time data platform. Besides what I've talked about today, we've also included the ability to do user-defined functions, to do compute within the server. This is a pretty important function, and it's one of the things that's, going back to Stonebreaker again, that he did quite well within VoltDB, is the ability to use user-defined functions to get flexibility. When Stonebreaker wrote the seminal paper that the database layer needs a rewrite, he prophesied a world of thousands upon thousands of new database companies, which was obviously prescient, because we're living that world now. However, we believe that user-defined functions allow customization of that database and allow you to solve different problems. Okay, let's say you've got a pub-sub problem. Great. Take your user-defined function, hook it up to your queue, and then be able to blast updates out. You've got a problem where you need to do a particular kind of Fourier transform over the last 24 hours of your data. Great. Store that user's data in place using a large data type storage system, and then write your own function to be able to do that instead of having to pull all that data out to an app server. All of those kinds of capabilities become unlocked with UDFs, as well as the ability to do the kind of MapReduce processing I was talking about. We're excited about adding a lot of that functionality, but we're not losing track of the fact that our claim to fame within a lot of our customer base is the extraordinarily predictable and reliable key value store aspect. So we're trying to add all that stuff in. You can get Aerospike both in Community Edition and in Enterprise Edition. So we are a closed source house, you may imagine that, except for our clients. So if you're using our client, you can all that is source available because you're going to be bundling it into your application server. And it makes sense for you to be able to do that at the source code level. The Community Edition, however, is pretty wide open, so there's no transaction limits, no time limits. You can go to production on it, but you only get community support, and you also have a data size per cluster limit that is currently at 200 gigabytes. So it's great for things like replacing, say, a Redis server that is not got appropriate clustering or doesn't use Flash, and then growing up from there. So hopefully I've hit all the points on my original slide. You can tell me if I did or didn't. But that's what we're currently looking at Aerospike in terms of bringing the power of analytics into that operational front end store.